So far in physics, you've heard about some abstract sounding topics. Newton's three laws of motion, inertia, acceleration, momentum, conservation thereof, impulse, collisions, recoil, even explosions. And wow, that's so much vocabulary, it might seem like information overload. And that's even before you get to the fact there's a bunch of math equations to go up with all of that. Well, before we get into nitty-gritty of tackling some problems, let's try to develop a deeper conceptual understanding of some of the underlying physics here, shall we? Also, remember, if you want to see the equations at any time during the video, you're more than free to go into the description below and download the equation sheet. Alright. So let's imagine now we have an astronaut floating in space with zero acceleration. What does that mean the net force on the astronaut is? Well, let's check our equation sheets. Force is equal to mass multiplied by acceleration. Therefore, if acceleration is zero, net force is also zero. Furthermore, what does the absence of acceleration imply about the astronaut's velocity? Well, acceleration is the change of velocity over the change of time. Therefore, if the acceleration is zero, that means the velocity must not change with time. Velocity is a constant. With no reference, we can't say what the constant velocity is, but for simplicity, let's say the velocity is zero with respect to this space station. Now here's the pickle. This astronaut is floating out in space and realizes her jetpack is out of fuel. She tries calling for help on her radio, but due to electromagnetic interference, her signal is scrambled. How can she get back to the space station? Things look bad. Throwing her arms about does nothing. To get back to the space station, she needs to gain velocity towards the station. That acceleration requires a force. This would be so simple back and off. You could just walk or swim, pushing against the ground or water to propel yourself forward. But out in space, there's nothing to push against. If only there was something to apply a force on me, she thinks. What to do? Well, she could throw one of her objects towards the space station. Maybe it will make a thud, and someone might hear her. Let's think about what this entails. To throw the ball, she must apply a force on the ball. But what does the ball do in response? We've learned that for every force, there's an equal and opposite reaction force. When she applies a force on the ball applies an equal and opposite force back onto her hand. If we look at the three body diagrams of each object, we see they both have one unopposed force acting on them. Therefore, they both have a non-zero net force. This means both objects will accelerate. Do the objects accelerate in the same direction? The forces are in opposite directions. Therefore, the accelerations will also be in opposite directions. So this means if you find yourself stranded in space or stuck on a very low friction surface and don't have traction, one way you could cause yourself to move is by throwing an object away from yourself, and the force of the object acting back on you will cause you to accelerate in the direction opposite of the throw. So if the astronaut throws her ball away from the station, she will move towards the station. We can relate the accelerations of each mass to each other by using the force on the ball is equal and opposite to the force on the astronaut. That force is equal to mass multiplied by acceleration to get mass of the ball multiplied by the acceleration of the ball is equal and opposite to the mass of the astronaut multiplied by the acceleration of the astronaut. One thing you might care about is how fast you move afterwards. To figure that out, we need to relate one of these quantities to velocity. Recalling that acceleration is the change of velocity over time, we can substitute this in to get mass of the ball times the change of velocity of the ball divided by the change of time is equal to an opposite of the mass of the astronaut multiplied by the change of velocity of the astronaut divided by the change of time. The time for both accelerations is the same because the objects are in contact with each other for the same amount of time. Because both sides are divided by the same change of time, we can cancel change of time from the equation and simplify to get mass of the ball times change of velocity of the ball is equal to an opposite of the mass of the astronaut times the change of velocity of the astronaut. This looks somewhat familiar? Mass multiplied by a velocity? You may recognize this. Take a look at your equation sheet. Mass multiplied by velocity is momentum. Remember, momentum is represented by the letter P. For a constant mass, an object's mass multiplied by the object's change of velocity is the change of momentum. The change of momentum of the ball is equal and opposite to the change of momentum of the astronaut. This situation, whenever two objects are pushing apart from each other, is what physicists call recoil, or if you like a flair for the dramatic, a explosion. Furthermore, if the change of each momentum is equal and opposite, that means the sum of the change of momentum of the ball and the change of the momentum of the astronaut is zero. The total change of momentum is zero. Well, that's good. Momentum of a system is conserved in the presence of only internal forces and no external forces. We can further expand this equation to be mass of the ball multiplied by the change of velocity of the ball plus mass of the astronaut multiplied by the change of velocity of the astronaut equals 0. Expand the change of velocity and rearrange to get mass of the ball multiplied by the velocity initial of the ball plus mass of the astronaut multiplied by velocity initial of the astronaut equals mass of the ball multiplied by velocity final of the ball plus mass of the astronaut multiplied by velocity final of the astronaut. That's our conservation of momentum equation for a collision. It turns out recoil is mathematically the same as a collision. In a collision, two objects start apart, slam into each other, and either bounce or stick together. However, in recoil, one total object breaks into smaller pieces that move apart. These equations we have found are tools we can use for a lot of momentum problems. Take a moment to appreciate that all of this math that we did without numbers came from one equation, force equals mass multiplied by acceleration, and one relationship that for every force, there's an equal and opposite reaction force. This is an excellent example of how most of the work in physics comes from manipulating and rearranging equations without using any numbers. If you're working on a physics problem on your homework or exam or what have you, this is an example of how to think and reason through a problem before using numbers, by first taking the physics you know to be true and working on from there. Now, let's take a look at a problem. A 60-kilogram astronaut is out on a spacewalk with a 5-kilogram space camera. While enjoying the view with zero velocity relative to a space station 50 meters away from her, she realizes her jetpack is out of fuel and only has 1 minute of air left in her tank. Part A. What is the minimum speed she must throw her camera to return to the space station in time? B. If the contact time of the throw is half a second, what force does she need to apply to return to the space station in time? And part C, what would be the answers to parts A and B if instead the astronaut was drifting away from the space station at half a meter per second the instant she throws her camera? Part A, I recommend re-walking through the derivation from this video to see if you can solve this problem from scratch on your own, if only given the relationship that force is equal to mass multiplied by acceleration and momentum is equal to mass multiplied by velocity. Part B will require you to rearrange and manipulate these equations in a slightly different way than I have in this video in order to solve, but I believe in your ability to do that. Part C will hopefully help develop your intuition for these type of problems by changing the initial condition and seeing how that affects the final outcome. I will be posting my own solutions in a separate video at a later time for you to check out after you've all hopefully walked through these problems. If you want even more practice, if you go to the description below, there is an additional worksheet with extra momentum problems, and you will also be able to find some lesson notes I've typed up to go with the content from this video.